Welcome to G Fun Facts Online, where we dive into the science behind everyday curiosities. Ever found yourself in an all-out brawl with a ketchup bottle? You know the drill. 1 second, nothing. The next, your fries are swimming in a Red Sea. Well, that frustrating, then messy moment is your personal introduction to the amazing world of yield-stress fluid dynamics and something called non-Newtonian materials. Stick around, because today we're uncorking the physics of ketchup and other stubborn liquids. So what's the big deal? Most liquids we think of, like water or even air, are pretty straightforward. They're called Newtonian fluids. If you push them, they flow. And if you push harder, they flow faster, pretty proportionally. Their resistance to flow, or viscosity, stays the same. But yield-stress fluids? They're the rebels of the liquid world. They act like solids when they're just sitting there, or if you're gentle with them. Think about toothpaste on your toothbrush. It stays put, right? It doesn't just ooze off. That's because it needs a certain amount of force, a yield stress, before it decides to flow. Below that magic number, it might squish a bit, like a spring, but it won't actually flow. Once you apply enough force, like squeezing the toothpaste tube, it gives in and starts moving. What's even cooler is that their viscosity can change depending on how fast they're flowing. This quirky behavior comes from a tiny internal network of particles or molecules that kind of interlock, like a temporary scaffold. Ketchup is the superstar example here, but you encounter these fluids all the time. Mayonnaise, mustard, whipped cream, mud, cement, some paints, and even our own blood. All right, let's get back to that ketchup. Its stubbornness, followed by that sudden gush, is down to a couple of cool non-Newtonian tricks. First up is shear-thinning. This just means that as you apply force and make the layers of ketchup slide past each other, that's shear, its viscosity, or thickness, goes down. So when you shake or smack that bottle, you're applying shear. This breaks down ketchup's internal structure, making it runnier and easier to pour. The harder you shake, the thinner it gets, at least for a bit. Then there's thixotropy. This is a bit like shear thinning, but with a time element. Thixotropic fluids get thinner the longer you apply stress. But if you let them sit, they'll gradually thicken up again. For ketchup, this is because of a network of tomato particles and long molecules called pectin. Shaking disrupts this network, it flows. Let it rest. The network reforms and it's back to being thick. Some scientists also classify ketchup as a Casson plastic, meaning it has this yield stress point and then flows in a specific nonlinear way. Believe it or not, the famous Heinz ketchup bottle was actually designed with all this physics in mind. Scientists even have a suggested technique. First, shake the bottle with the lid on. This gets everything mixed and ready. Then, turn it upside down. Finally, tilt it and tap gently, increasing the force until your ketchup gracefully flows. No more ketchup explosions. Yield stress fluids like ketchup are just one part of a bigger, fascinating family called non-Newtonian fluids. Basically, these are any fluids where the relationship between how much you push, shear stress, and how much they flow, shear rate, isn't a simple straight line. Besides our shear-thinning thixotropic ketchup, there are other types. Ever played with oobleck, that cornstarch and water mix? That's a shear thickening or dilatant fluid. It gets bouillongs viscous, or thicker, the faster you try to move it. Punch it, and it feels solid. Move your hand slowly, and it flows like a liquid. Then you have viscoelastic fluids. These guys show off both liquid-like flow and solid-like elasticity. Think of dough or even cheese. And there are Bingham plastics, a specific kind of yield stress fluid. Once you overcome their yield stress, they flow with a consistent relationship between stress and flow rate, kind of like a Newtonian fluid but with that initial hurdle. Mayonnaise and toothpaste are often given as examples. For more complex situations, scientists use models like the Herschel-Bulkley model, which can describe fluids that don't flow so linearly after they start moving. So why do we spend time studying these quirky fluids? This field, called rheology, the study of how stuff flows and deforms, is way more than just understanding your condiments. It's huge. In industrial processes, making everything from food like sauces and dairy to cosmetics like creams and gels, pharmaceuticals, paints, inks, ceramics, and cement relies heavily on understanding yield stress. Think about paint. You want it to flow easily off your brush, but then stay put on the wall without dripping. That's yield stress at work. Pumping, mixing, coating, and filling containers with these materials efficiently all depends on knowing their flow properties. In geophysics and civil engineering, understanding how mud, debris, lava, and wet concrete flow is vital for predicting natural disasters, designing sturdy buildings and bridges, and even in drilling operations for oil and gas, where special drilling muds are used. The yield stress of mud can determine if a mud flow stops on a hillside or keeps going. Even in futuristic tech like 3D printing, many materials used are yield stress fluids. They need to flow smoothly through a tiny nozzle and then firm up quickly to hold their shape. And of course, in everyday products, that satisfying texture of toothpaste staying on your brush or mayonnaise holding its shape comes down to yield stress. It also helps keep particles from settling in products, improving their shelf life. Despite how common these fluids are, their behavior is incredibly complex and still presents big challenges for scientists. For one, precisely measuring the true yield stress isn't easy. The values you get can change depending on how you test it. Developing accurate mathematical models to predict their behavior is another tough nut to crack. The way they switch from acting like a solid to a liquid creates tricky points for computer simulations. And it's not just about how they flow when sheared, like stirring. How they behave when stretched, what's called extensional rheology, is also super important for many applications and is a hot area of research. Scientists are also working hard to understand how the tiny, microscopic interactions between particles or molecules create the flow behavior we see on a larger scale. Plus, that time-dependent behavior of thixotropic fluids like ketchup and how these materials age or change over time adds another layer of complexity. But the research is exciting. Scientists are developing more sophisticated models that include effects like elasticity and thixotropy. They're improving simulation techniques. Research networks are popping up to connect academic and industry experts to solve these puzzles, aiming to bridge the gap between fundamental science and practical uses. Studies are looking into things like how bubbles behave in yield stress fluids, which is important for industries like managing oil sands, or how drops of these fluids interact with surfaces, key for coating and printing. Interestingly, some research shows that for certain types of yield stress fluids, increasing their yield stress can actually make their flow more stable, which is the opposite of what happens with simpler Bingham fluids. So the next time you're patiently, or impatiently, waiting for that ketchup to make its grand appearance, remember you're witnessing a fascinating bit of physics in action. From that simple bottle, we've journeyed into a world of complex fluid dynamics that impacts everything from the food we eat and the products we use to how we build our world and predict natural events. The study of these unyielding yet essential materials is constantly evolving, promising even more innovations in the future. Thanks for tuning in to G Fun Facts Online. Join us next time for more deep dives into the amazing science all around us. Don't forget to subscribe.